the mechanisms of recombination, whether direct and indirect, they are important at thermal equilibrium or with a steady state generation recombination process going on in balance. For example, if a semiconductor is at equilibrium, thermal equilibrium, and then it faces generation of EHPs at a rate, let's call it GT, which is generation happening with the respect to temperature. So we call it GI, or we know we looked at it before, it would be sigma R Ni squared, where sigma was the recombination rate constant. And now this would result into optical. In case when we are using light, we would call it optical generation. So that would be now on top of what is the thermal generation happening. So we have to add them. Now in this case, this sigma R will become a new value, which now depends on not just the thermal regeneration, but also the optical regeneration as well. Now, on the other hand, we have to update this equilibrium values with adding the sigma N and sigma P as well in the, I think it's delta N and delta P as well, right? So we have to update that. Now, if there is no trapping and there is a steady state recombination happening, which is direct case, we can just simplify the right hand side, and what we end up with is this relation. Now, if it is low level excitation, this is very small and this is even smaller than that. So we can neglect that, we can ignore that, and that simplifies our relationship. So our change in the carrier concentration is now a function of the optical generation and carrier lifetime. So this relationship is very important because this is what contributes to the excess carrier concentration, both cases, p-type or n-type. But you have to remember that we can use it for cases when it is equilibrium, but generally tau n is not equal to tau p. And this is something which we saw last time, that how do we calculate, but you have to remember that was the case for low level injection. But generally these are, in that case we could call them equal, but when you talk about high level injection, then especially when traps are present, that's the different lifetime constants for both of the case, especially when traps are present. So then we cannot generalize them to be equal, right? So now if we have a notion of generation of new charge carriers, if you think about it, previously the presence of n-type or p-type, presence of electrons and if this was EI, the presence of electrons or holes was, we could know from the Fermi level value, right? So if EF was close to EC, we would call it n-type. But now when you have steady state carrier generation happening, we are also getting, even if you look at this material, this would become like this, where now in addition to EF, here we are getting a level which is telling us that there are p-type or holes are also being generated at higher level. So what do? There is only one Fermi level, but now we have the presence of holes also in this case. So if it was n-type, but now we have holes, how do we show them? So we call this case as quasi Fermi level. So quasi means something which is, we suppose something, or something where we do approximation. So hence what we have to do is we have to introduce steady state electron or hole concentrations in the band diagram by introducing what you call as quasi Fermi levels. So you have to remember, and we would write it as Fn and Fp. I'll come to this example later on, but what I want to share with you is, instead of writing just EF, now we will write them as Fn and Fp, and these are called quasi Fermi levels. So when do we have quasi Fermi levels? When we do steady state optical generation, or it can be by any means, but the bottom line is when we have steady state carrier generation, which is more generally we can call them excess carrier concentration, which is both n-type and p-type are being created. So in that case, that is depicted by the presence of two Fermi levels, one depicting the presence of n-type carriers, the other depicting the presence of p-type carriers. So now this picture is what is showing originally a material which was n-type. How do I know that? Because I'm writing EF. So there was an EF there which tells me it was n-type. But when we expose it to excess charge carrier concentration, excess charge carriers generation, it resulted into many holes also being generated. So in that case, we introduce a quasi-Fermi level and we call it FP, close to EV, and we write EF now as Fn, which now tells me, and you have to remember quasi-Fermi levels will be in pairs, and this is now almost equal to the original Fermi level. Of course, there's a slight increase, but and slight increase means this has moved just a little bit close to the conduction band, but it's almost the same. We can ignore that. So you have to remember when excess carriers are present, instead of having Fermi levels, we have a quasi-Fermi level. So in that case, now our relationships gets updated where instead of Fermi level, we use now quasi-Fermi levels. So in this case, now we will be able to calculate exactly how many charge carriers are there at equilibrium. So we have to remember the same relationship that we have seen before are now updated when you have quasi-Fermi levels. And quasi-Fermi levels are introduced because we are having steady state electron and hole carrier concentration generation. We have steady state electron and hole generation happening, which has to be covered now by including Fermi levels close to both EC and EV. And in that case, these are called Fermi levels. It's not EF now because EF was only when there was no excess carriers present. But now we have steady state concentration of both of them, which needs to be now shown with what we call as quasi-Fermi levels, and we write them as Fn and Fp. Now here's an example for a question that if you have optical generation happening where we have 10 raised to the power 13 electron hole pairs, which is electrons over pair at this rate, pairs per centimeter cube per microsecond, and your steady state electron concentration is 10 raised to the power 14. We can calculate, this is given for silicon at 10 raised to the power 14, going back to that relationship, not relationship, this figure for 10 raised to the power 14, we can find out how much is the carrier concentration. And from that number, or it will be given in the question, let me take care of these. There are too many of these lines here. But you know what we have been going through if you have followed the lecture. So using that relationship, I can find out how many carriers are being generated. Now, if I know steady state excess carrier concentration, I can find out minority carriers. This is the majority carrier given here. With this, I can find out the minority carriers. And then I know how many of these are being generated. So this is the same number which is being generated for the holes also. So in this case, now finding the total is just the concentration which is there because of the doping plus the concentration which is being now generated because of the optical generation. So with these two, then we can find out the total steady state carrier concentration for a material. If you look at it, this is not what you would have at equilibrium just because of doping. This is now much higher than that. So that tells you why we want to create quasi-Fermi levels. Think about it. This is now 7 orders more than the background minority carrier concentration. So now at equilibrium, we use this, but when you have excess carriers happening, then they cannot be, this relation cannot be used there. This can be used only to find equilibrium, but you have to then find this separately, and you have to add this into what you would find at equilibrium. I want you to know this, what I'm talking about, because it's a very important distinction. When you have excess charge carriers, you cannot use the value of the charge carriers due to generation. You have to first take the steady state carrier concentration. From this, you have to then find out minority carrier concentration, and you have to use these two values to find what is the excess that is being generated, and that excess would be equal to, they will be equal because it's electron hole pair formation, right? And that's the number then which needs to be added to steady state value, and that would give you the final number of how much are the minority charge carriers now after this optical generation has happened, right? So this is an important message from this, because this enforces this idea that we cannot just live with the Fermi levels now. We have to update Fermi levels into quasi-Fermi levels, and that is more realistic understanding of what's happening. So this question is again telling us that at steady state, this example is telling that steady state steady state charge carrier concentration is this much, which is a combination of these two, right? Now this we have to plug in here to find our Fermi level value, Fermi level of the Fermi level. So our relationship is now updated. When you are dealing with this, we don't just use N or P. We would use now N would be N naught plus sigma N, or P would be now P plus sigma P. That's what we have to use now when you are dealing with quasi-Fermi levels. So you have to remember, when you see a question in the exam or when you are solving a problem for homework, you have to see if there is an optical generation, electron hole formation happening. If that's happening, then this is the thing that you have to use to calculate the Fermi levels, right? All right, so let me summarize this. So in summary, the quasi-Fermi level Fn and Fp are the steady state analogues of the equilibrium Fermi level EF. And this is only to take care of the excess carriers, which means both N-type and P-type, which are being generated because of the generation process. And their population now is different from the equilibrium population N0 and P0. And this concentration of excess EHPs that causes a larger shift in the minority carrier quasi-Fermi level